Good morning, everyone. This is Koreanski. I am screencasting from my home office. Our research deals with runtime verification of embedded systems, especially Internet of Things systems that are resource constrained. We are particularly trying to make runtime verification available by using complex event processing. Let's go over some of the basics in our research. Runtime verification is a method for checking whether a run of a system satisfies or violates a given correctness property. A correctness property is actually what a system is required to do when it is run on an actual deployment environment. So this is a complementary testing or verification method. A run of a system can be defined by a finite sequence of system execution traces, which can be acquired by logging system traces. Execution trace is generally described in terms of state transitions, and we are going to exploit this fact because a state transition can occur by the events occurring in a system. So we will try to define or specify a system in terms of events so that we can exploit complex event processing for verification, runtime verification purposes. In runtime verification solution, the correctness properties are monitored by runtime monitor, which is a software program that reads the finite traits and yields a certain verdict, a decision about the correctness of the property. It can be either true, false, or inconclusive. So runtime verification itself deals only with the detection of violations or satisfactions of correctness properties. You can do either online or offline runtime monitoring. What do we mean by that? In online monitoring, you execute runtime monitors at the live system. So it listens, it observes the vitals from the running system. In an offline monitoring scenario, you record the execution traces of a running system, then you apply the monitoring algorithms. In another setting, runtime monitors can either be intrusive or non-intrusive. In other words, it can be non-instrumented. A system might be non-instrumented, or it might have to be instrumented in order to acquire some execution trace from the system. So we are proposing that we will be developing a non-intrusive runtime verification methodology so that we don't insert any performance or behavior overhead, or any behavioral change on an actual system. So we prefer online and non-instrumented runtime verification. What is complex event processing? It's a technique originally introduced for deducing complex decisions in business processes. So it enables us to make high-level decisions about event-driven systems. In an event-driven system, you have tons of simple events, so you can use transitions, transformation functions, aggregation functions, and filtering mechanisms in order to get complex meanings from those groups of simple events. So any software system can be described, any software system with function calls can also be described as a collection of events, because any occurrence of a function call can be described as an event. So traces of simple events can be synthesized to obtain information about runtime behavior of a system as compared to its expected behavior. We are going to use an open source complex event processing engine called SPAR. It is written in Java. There's a C# implementation as well. It is called Nesper. It helps us to define express filtering, aggregation, and join mechanisms by using a rich event processing language. Since we are dealing with Internet of Things systems, as we stated earlier, these are resource-constrained devices. We decided to come up with a solution, particularly for those resource-constrained devices, and there is a particular application layer protocol for such devices, which is called CoAP. It's short for Constraint Application Protocol. So in a CoAP environment, there are two participating endpoints in a communication. One acts as a client and the other one acts as a server. Any endpoint, any participating party in a communication in CoAP domain can both act as client or server. This is an asynchronous messaging environment, and it relies on request-response messaging model. So, if a client requests any information, any service from any other CoAP server, it simply sends a request message to the particular server. Then the server responds with an appropriate response message. So we can say that the CoAP system's execution trace consists of sequences of request and response send messages. Before going into how we describe these basic ideas in a complex event processing environment, we need a mechanism, we need a middle step in order to describe a system in terms of events. In order to do that, we are going to use event calculus. In Gene world, we use natural language assertions to indicate an occurrence of an event. For example, if you say the weather turned rainy, it means that it started raining. This is an event, and it indicates a state change. So, by exploiting this fact, Kowalski and Servot introduced event calculus to help specify information systems in terms of events, so that we can capture temporal relations amongst occurrences of events. And in this calculus, in order to capture the time-varying properties of a system, they represent the idea of fluents. You can refer to the references part of my paper to get a detail on the event calculus. This is a short list of simple event calculus predicates. Predicates are used to identify event occurrences. For example, initially in a system, a fluent might be true or false, right? So a fluent, a time-varying property, might be altered by occurrence of an event. So in order to represent that, we can use this initiates function, initiates predicate function, and some other event might terminate a fluent, and this can be represented by this terminates predicate function. In the example given above, for example, let's say we have a fluent about weather condition. Initially, we might say that it is shiny, but in an event where it started raining, then fluent becomes rainy, right? So this function can be used to represent that. So let's see how we can use this simple event calculus in representing an IoT system in terms of events. Interactions between components of an IoT system can be represented as events if we can represent those in terms of event relations, simple event relations. Let's try to define a new predicate for temporal ordering relation between consecutive events. The following function, follows function, represents a simple relation between two consecutive events, E1 and E2. We are using happens predicate functions. In the first, this indicates that E1 occurs at T1, and this indicates that E2 occurs at T2, and T1 and T2 has a relation such that T1 is less than T2, so it means that E1 occurred before E2, right? So this can be used to define sequential ordering between any pair of request-response messages. So if you consider that CoAP is a request-response message, then we can use this predicate function to express temporal ordering between any two CoAP messages. A fluent for this particular domain can be defined as follows. A fluent is initiated with the occurrence of an event, and it will be true until the occurrence of another event that will terminate it. So we will state that a fluent holds that will be true in between these two events, right? And we will try to use these predicate functions in a case study. We selected wireless token ring protocol because of its simplicity and it relates to the audience of this conference. So in order to discuss runtime verification, we first need to make a system. We first need to make or define a system specification for this particular case study. We will state that as a specification, token ownership is released and acquired in an increasing mode ID order. This is our design, so it's quite simple, but as we said, it is for the sake of simplicity to give you the idea. And we can define new predicate functions for each domain that we are dealing with, and we can use these predicate functions as fluents in our event calculus, because the values of those predicate functions will be dependent on the time. So take this predicate function. This indicates token ownership. It states that token ownership for mod mx at time tn is 1 if and only if mod mx owns token at time tn, right? And we will assume that mod 1 initially owns the token, so to of m0 is 1. And we will define another predicate function, order of ownership. We will assume that order of ownership is preserved at all times, so OT is always 1. And we will try to define a concrete correctness property such that it will help us to define EPL statements, as per processing language statements that can be used in as per ng. So this is the correctness property. It's a long one, I know, but you can see the details of it. So it states simply that a send message occurs. Two consecutive send messages occur between from two different modes, and if you observe that the later mode ID is 1 greater than the previous mode ID, then this holds that predicate function holds true. So this relation must be observed in all send events. Let's see how we implemented that in our experiment. We've used open source packages, applications in order to develop our solution. We've used JPCAP library in order to capture network capacity packages. Then we altered some part of Californium, which is an open source implementation for web browsers of web protocol. We produced simple QUEP events, and we inserted those QUEP events into an Esper engine, and we analyzed the event calculus in order to create EPL statements of these lines, as you see. So these are EPL statements that we insert into Esper engine as the simple events are produced from QUEP network. Those are fed into Esper engine. Then these EPL statements are executed, exerted on them one after another. This is the results. This is the number of Kuja events. Kuja is a simulation environment for quantity operating system. This is the number of Esper events that we captured in Esper, so on and so forth. So this is the performance result. The performance result is attained by dividing Esper faults to Kuja faults. As you see, most of the faults are captured, but we think that some of the Kuja packages, packages are lost at the network layer. So we are going to deal with those later. And this is the conclusion and future work for my study. Thank you for listening to me.